Today we will be doing a gravity quiz. Let's do a quick little review and then we'll hand it out. For the D3 students, your teacher should have a copy and you'll just take it and then they'll have to do their best to correct it, I guess. So, just a little bit of review. What is the equation for the force we feel due to gravity on the surface of the Earth? Good. W equals mg for force, because this is the acceleration due to gravity on the Earth. So there's one thing we need to remember. Then, what's the equation for gravity?
G equals G over R squared.
Over R squared for the force of gravity, sorry. So F equals GMM over R squared. Gravitational constant. If you're not given it, just leave it as G. Actually, I'll write it on the board during the quiz.
6.67 times 10.
Yeah, it's 6.674 times 10 to the minus 11. Yeah, I'll leave what G equals on the board. Those are the masses, and this is the distance squared. Do you remember how we found the acceleration due to gravity on like Venus or something?
Sure.
So force equals what? Mass times acceleration, right? So if I'm trying to find the acceleration on a planet, don't I just cancel the masses?
I guess so. Yeah, so just to clarify, you take gravitational constant, which is...
So on one of the problems you're doing on the quiz, it will say use 6 times 10 to the minus 11 to figure it out.
So you do that times the...
Mass times the mass divided by the distance squared.
divided by the distance.
But for acceleration, it's just this constant times mass divided by the distance squared for just the acceleration. Okay? And it's going to ask you to set it up and not solve it, meaning you just put in the numbers, but you don't need to calculate it. Okay? So in your quiz, it's going to ask you to do that. Yvonne, it should be uploaded online. So I uploaded a copy for you to take, so you can go ahead and start taking that if you want. Any other questions before I start, though? And then what is G on Earth? 10 or 9.81 meters per second squared. I'll take either one because we've used both of them. All right, should take about 15 minutes. D3 students, you're just wait, and then your teacher should collect it when you're done. Okay, so it's awkwardly just going to be quiet on this video for... Actually, I'm just going to pause it there and then upload it. It's easier just to upload one video. So you guys are going to have 15 minutes-ish of silence. Yes?
Are we grading it in class, or are you going to grade it?
I'm going to grade it. I feel like that's a little bit less stressful.
Yeah.
Okay, so you have about 10 to 15 minutes. Actually, I'm going to stop this video and I'll just upload 2 of them. Sorry, I'm thinking out loud. No, it's faster if I upload one. So, oh, yeah, sorry. You'll only need this for the last one. So if D3 students, I did end up cutting this into 2 segments, so if you still need time, just have your teacher pause it until you're done and then continue with this. But now, let's go ahead and get into the back of the spring packet. I think we were just going to go over 6 and 7, and then I kind of want to talk to you about some more advanced stuff, but it's interesting, and then kind of front load our next lesson. So page 6. Oh wait, guys, get it out. Da, 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 da. Well, I guess first. Oh well, I can't do that. Never mind. All right. What is Hooke's law equation?
F equals negative
And again, this negative is just to mean it's the opposite direction of whichever way I'm stretching the spring. So if I move the spring in the positive direction, the force is negative. If I move the spring in the negative direction, if I elongate it, if I stretch the spring, the force is negative. If I compress it, the force is positive. What is the equation for weight?
W equals mg.
Good. W equals mg. Did everybody get that on the quiz, hopefully? Well, good. You got 1 point. That's 8%. All right. A force of 20 newtons is applied to a spring. How much is the force on the spring? Include the direction.
Negative newtons.
Negative 20 newtons, right? So if I'm pushing on the spring with 20 newtons, then which law says that it's negative?
Second. Third. Whatever. one
First,
is
second,
that.
third, fourth, fifth?
Third.
Third. Every action has an equal and opposite reaction. So that would be the third law that lets us figure that out. All right, a spring has a force of negative 30 newtons, so we're on number 4 on page 6. A spring has a force of negative 30 newtons. Is the spring compressed or stretched?
Stretch.
Stretched, good. If it's stretched, it's negative. All right, now we're going to try an actual equation.
Ooh.
Oh, I
I
know.
know the answer is negative 10,000 newtons.
Negative 10,000 newtons.
Yeah, that's what I got, right?
A spring constant is 50 newtons per meter and is placed from its resting position by 20 meters. All right, so are we given force in this equation? No, we are not given force. We are given, the spring constant and the distance. So the spring constant I'm going to go ahead and replace with 50 newtons per meter. And then it was displaced by, 20 centimeters. So we should get 1,000 newtons, right?
Yes.
Sure.
Wrong. What do I need to change?
Well, it's negative.
Nope, not the negative.
Oh, the
And
centimeters.
it's
Centimeters. Got to make sure I change that to meters, right? So this would be 0.2 meters. 2.2 meters. And then this would end up giving negative 10 newtons. The force of the spring would be negative 10 newtons in this case. So basically, if I stretch it to 20 centimeters or 0.2 meters, and then let go, it's going to have a force accelerating it in that direction. Okay. A force is used to compress a spring of unknown spring constant by 20 centimeters. So we're using this equation again. All right. Now, what are we given in number 2 right here, Kaylee? What information are they giving us? Good. So I'll replace F with the force, which is 2,000, right?
Yeah.
Then
The X.
it's compressed.
So X. Is
So if it's compressed, is X positive or negative?
negative.
So think about a spring.
Negative.
If I compress it, is that moving in the positive or negative direction?
Negative.
Negative, right? So this would be negative 20 centimeters. Now, what's kind of weird here is we actually do not have to convert this one because we can say newtons per centimeters.
You're right, I forgot about that.
But let's go ahead. We can change it to meters, right? This is 0.2 meters.
No, don't change it.
I'll leave it in centimeters. It makes the math a little bit
You
easier.
already have the answer.
So I divide. These negatives will cancel, right?
Yeah.
So it's basically going to be 2,000 newtons divided by 20 centimeters gives me K, which would give me, so K would equal 100 newtons per centimeter.
Yeah.
If you did convert to meters, you should end up getting 10,000 newtons per centimeter. All right, number 3. A force and a constant. So what am I trying to figure out in this one? The displacement. Good. So the force is 55 newtons, 550 newtons, The spring constant is 50 newtons per meter. And we're trying to find x. Just divide both sides by 50. You get 11 negative. Sorry, I forgot my negative. Negative 11 centimeters? Meters. So that spring stretched 33 feet, about. Pretty big spring. Probably not super realistic. I've never seen a spring that big. Maybe they have them on like aircraft carriers, those things that catch the jets when they land. But I think that's actually a pulley system. Anyway. All right, page 7. Does anybody want to come up and draw? Oh, wait, I can't have you come up because I don't know if I can film you and put you on this. So, never mind.
Draw it over there and then like show the camera.
Yeah, we'll just
Go
start right there.
and then
You can show it or something. Students. Cover the camera first.
You guys can just tell me what to do because your voices are pretty anonymous. All right, there's 2 forces working on this object. Lily, give me one of them.
Would it be
Yes.
force of gravity?
Good. The force of gravity or weight, which is mg.
Normal?
And then the other one, it's not the normal force in this case because it's not resting.
Oh.
K. I don't know.
Yes, it's the force with that in it. What force is that?
I don't know. Spring constant.
Spring force.
I'll memorize it as K.
The force with the K in it, yes. So the spring force. So there's the free body diagram for number 1. These are equal and opposite because it is at equilibrium. That just means it's not accelerating. And this is equal to negative kx. All right, number 2. The mass of the load is 0.5 kilograms. What is the weight? So I'm just going to use W equals mg. The mass is 0.5 kilograms. G is, what do we use for T? G?
10
10, good. 10 what?
meters per second.
Good, meters per second squared, giving me 5 newtons. Ooh. Yeah, that's fine. Number 3, obtain the force of the spring. So, what are we going to replace Fs with? So we have the force of the spring is negative kx. We got to replace some things. If the weight is 5 newtons, and this is at rest, the force of the spring has to be negative 5 newtons. Good. So this would be negative 5 newtons because it's in the opposite direction. If this is positive down this way, this has to be negative that way. And then negative, the spring constant is 10 newtons per meter. Times x. What's 5 divided by 10?
1/2.
1/2.
Yeah, okay.
0.5 meters would be the stretch. And in this situation, we're saying down is positive, which is fine. We can do that. That's not a big deal.
That's the next problem.
Oh, obtain the force of the spring. That's number 4. Sorry.
I knew it.
That's number 4. You guys should yell at me more. All right, number 3. The force of the spring is what? Negative 5 newtons. Because it's equal and opposite. I kind of answered it
Yeah.
while I was talking, just not in the right order. So this is how you solve the problem. Now what I want you to do is take, 5 minutes. See if you can solve 5 by yourself. And if you've already solved it, let me come check. So see if you can solve the last one. Take it about 5 minutes to try that. Oops. We're just trying. So I know this is weird. I'm recording and talking to a person online. So we're trying number 5 on page 7. We're trying the last one. But you just gotta draw a free body diagram and try and follow this as messy as it is. Yeah. So first, just draw a box with 2 arrows out of it.
Oh.
Did you already get that one? Well, you're trying to find how far the spring moves. Oh.
Done. You should come and check it.
We'll have to do it in my head real quick.
Okay.
Perfect. So what are the two forces that we're working towards?
Here we go.
Yeah. So we get weight, which is mass times gravity, and then we'd also have the spring pulling up. So I would write like W equals mg, because that's how hard it's going to pull down, right? So what's the mass? So we can replace m with 400. Weight does equal weight, that is true. And 400, then what do we use for g? Good. This will give us 4,000 newtons. Now, if the weight's down to 4,000 newtons, how hard is the spring pulling? Good. And then equals kx.
We still do need the weight. The weight is force. So
No, now we gotta replace k with what k is.
we're gonna get F equals negative x. And then the force would be whatever it is. So
Equals 4,000.
negative 4,000 equals negative 1,000. How did you get it? For weight, 400,000.
So
So
actually,
oh, that's what it is. I had these two together instead of actually. So it's so then it's 4,000.
oh, what's 4,000 divided by 1,000?
Negative 1,000 x.
Yeah. Okay. What'd you get? Good. Good.
Wait. No, the second variable is x. You're trying to find the second variable in the
I have it from X. So then it's 4,000 divided by 1,000.
Meters. All right, let's try this one. So this is where I think physics gets interesting, because now if you pay attention, we're actually using a ton of different things. We're using Newton's laws, we're using force equations, like we're using springs, and we're using gravity, and we're just setting everything equal to each other. So the free body diagram, we get something like this. You have weight equals mg down, and then you have the force of the spring, which equals negative kx up. Then, so that was part 1. 2, we found the weight, right?
Mm-hmm.
Which was 400 kilograms times 10 meters per second squared. Give me 4,000 newtons.
Yep.
All right, so now we know how much the spring would be. It'd be the opposite of that, right? So it'd be negative 4,000 newtons.
Mm-hmm.
And then 4, I substitute this into the spring equation. Negative 4,000 newtons equals negative
1,000 newton.
1,000 newtons per meter
X.
times x. Divide this side by negative 1,000. Divide this side by negative 1,000 newtons per meter. And then if you think about it, newtons cancel, and then 1 over meters down here would flip the meters to the top. Or you can just be like, it's distance, so it's meters. That's probably an easier way to think about it. So 4 meters would be the distance. So we used free body diagrams, weight, and spring to see how far the spring would stretch. And this is what engineers do in more complicated systems, because generally engineers aren't like, oh, a spring. Usually they have like hundreds of springs and gears and all these different things. But, so imagine doing this for like a bunch of different moving pieces together and seeing how much things should stretch. Or also, if we had a force from a spring, we could see how much acceleration an object would have at the beginning. And then it would kind of get less. So those are some of the kind of interesting things. I wanted to go a little bit deeper into springs. This isn't in the packet. This is just going to be kind of some extra information which I do from time to time in this class. So, yeah. Multiple step problems to try and figure out how far a string stretches. But there's a lot of things going on there. So now what I want to imagine is, let's say I have this block on a spring. I know my springs are beautiful. Now, let's say we're going to ignore friction. Okay, so nothing, no friction, no momentum's being lost or energy's being lost. We haven't learned about energy, but I still kind of want to talk about this a little bit. Then let's say I pull it some distance away. And I'm trying to make a graph of force times time. So let's say I pulled it in the positive direction. So the force would be negative, right? We could put some numbers in. I don't know, we could say K is 10 newtons per meter and X was 1 meter, just to make it easy. So the force that feels at the beginning would be negative 10 times 1, which is giving me negative 10 newtons, right? Isn't that the force it would feel? Let's say I just stretched it a meter, and then that's the spring constant. All right, so it would start at negative 10 newtons. Does anybody have a guess? If I expanded it by a meter and I let go, how much would it be compressed by? So if you think about it, right when I let go, what would happen? It would start speeding up, right? So it'd speed up and speed up and speed up until it hits its equilibrium point. Correct? And then it would start to slow down. So wouldn't the force slowly go to 0 until the spring's not compressed?
Yeah.
And then it would start to compress the spring. If nothing changed, like no energy or whatever, you don't know what energy is yet, but if nothing about the motion changed, just as a guess, how much do you think it would compress on the other side?
Not all the way, because there's still springs away.
Well, it would not all. Well, it wouldn't compress all the way, but it was stretched by a meter. So how much would it compress by?
A meter.
A meter, because it would essentially have enough momentum in the middle that the force it would take until you had the same amount of force applied to stop it again, and then it would start accelerating it the other way. So the way that the graph would look actually would be something like this as time went. So that would be what the force is doing. Essentially, the force gets weaker and weaker, hits 0, and then it becomes positive, and then it kind of hits a peak and comes down, and then goes up. What this actually starts to look like, if I let go and I change this from force to acceleration, to velocity, where would it be going the fastest?
The beginning.
So let's say I stretch it all the way out,
Yeah.
and I let go. Would it be going the fastest there?
It would be at the fastest at where it would normally set at rest.
Yeah, so it'd be fastest in the middle where there's actually no force acting on it. So it would actually, where there was no force, this would be, let's say we change this to velocity now. If this is a velocity versus time graph, the velocity would actually be 0 here, and then it would hit a max where the force was, and it'd look something like this.
And then it slowly get smaller and smaller.
Yeah, so this would be the velocity. Now I want you to think of another one. What if I tried to graph position here? So where does it start at? It starts away, doesn't it? So wouldn't it start here?
Yeah.
And then it hit 0 about here, then it'd start to curve out and wait, no, where would it max? Oh, sorry, wait, I gotta think about this. So it'd start there and then it'd be basically sinusoidal, so it would have to go. The velocity is 0 when it's at its farthest. Yes, I'm doing this right. So there are actually two different waves. One's the position and one's the velocity. This math, and the math is more complicated, I was just trying to give you a picture of what springs are like, but the math that solves a spring oscillating, it's actually, it's the same math that describes waves going through the ocean. It's also the same math of how sound goes through the air. There's some other factors in there that makes it a little bit more complicated, but this is the general idea. It's also the same math for how fast something is rotating. Can anybody have any other ideas of like something that's like going up and down? What else could this math describe? This graph? No ideas?
Figure eight.
A figure eight? No, a figure eight would look a little bit different than this. What about somebody jumping on a trampoline? And this is their height above and below the trampoline. Or pressure in a piston, like a piston in a car, right?
Yeah.
Compresses it, explodes, comes back, explodes, come back. So this is called oscillating motion. An oscillating motion is just caused by a force that's basically pulls things back and forth, like a central force, which is also gravity. This can also be the distance around a planet as time goes. No, that would be more like a comet, but it would be a little bit different of shape. This is also the math that would describe how fast you can hit something and what frequency it would want to vibrate at before it would break. It describes molecules throughout a table, how they would vibrate. So this really, it describes a lot about the universe. And so, I mean, that's kind of all I had for today. So, thanks.